Hello, I'm Gil Carlson, Director of Technical Services for ITT Fluid Handling Division. And we shall discuss during this section the application of system curves to pump selection for closed-loop piping system. The application for system curve usage is to establish the system curve from known values for a particular system as to flow and head. In this circumstance, and for an example, we're going to use a design point in terms of a particular system of 80 gallon per minute flow rate at 40 feet of head loss. So we can establish this then as the design flow head point. 80 gallons per minute at 40 feet of head. Now, head loss will change in the system as flow changes in that system. And the head that will be developed, we can call new, is equal to the design head times the flow rate change in the system, which is Q sub N divided by Q sub design, and that quantity squared. What this is really saying is this, that if we reduce the flow rate in the piping system, our head loss must necessarily decrease, and it will decrease as a squared function of the flow change. So if we have started out with a flow rate of 80 gallons per minute and we cut that flow rate in half down to 40 gallons per minute, we will have 10 feet of head rather than 40 feet of head, because we have squared 40 divided by 80, which results in 1/2. The 1/2 is squared. That half squared times 40 is 10 feet. So we then have 10 feet as a new flow point. Now, by using a calculator, we can very easily assess, through use of the formula illustrated, as to the new heads that would occur with changes in flow rate for this particular piping system. And by interconnection of those points, we can establish what is called a system curve. By plotting of that system curve on the pump curve, we can assess as to the actual operational point of that particular pump on the particular system described by the system curve. And the actual point of operation will be at the intersection of the system curve with the pump curve. And this is because of the first law of thermodynamics, which states that energy in must equal energy out. So the point of operation then must become the intersection of the system curve with the pump curve. Now, this knowledge can be used for determination of the impeller size required for a particular piping system, for a particular pump on a piping system. For example, supposing that we have an already installed pump, and that pump specified for a design flow rate at this point is actually pumping much farther out on the curve. We can then describe a system curve through the series of impellers allied with that particular pump and establish in a very simple way as to the impeller diameter that will match the flow rate need in terms of impeller size. We can also establish for a series of stock pumps as to how much flow would be provided by each of the stock pumps illustrated as an example in a catalog. And in this circumstance, we have a design point as illustrated, which is between pumps A and B. But we strike a system curve through that design point, and we can establish that with the smaller pump we'd be flowing in this circumstance at 105 GPM, and with the larger pump at 122 GPM, whereas our design point is 115. So that we could then really use the smaller pump should we so desire, but the generality would of course be to select the larger pump. Now, supposing that we have two pumps in parallel, each of the pumps being of equal size, and we want to select a pump for the parallel application, one pump being applied in terms of parallel application, the pumps being equal in size. So we can start out then noting that if pumps are in parallel application, each pump must provide 1/2 the flow rate delivered to the system, and that each pump must operate at the same head. So we can then take the basic flow point at some determined foot head, simply double that head, and establish a second curve, which is simply a doubling of the single pump curve. And this would then establish that to the system, when both pumps are in operation, it would appear to the system that we're operating with a single pump curve as developed from the addition of the two pumps in parallel. Now then, the question is, what happens on a parallel pump application when only one pump is in operation? And this is defined again by the system curve. This illustrates the developed curve used for parallel operation as developed from the single pump curve. We strike a system curve through that and can determine that if both pumps are in operation, they'll be operating at point number 1. Each pump, when both pumps are in operation, will be operating at point number 2. But should we shut off one of the pumps and operate with only a single pump, that single pump would be operating at point number 3. Now, operation at point number 3, of course, requires higher horsepower than operation when both pumps are in operation and operating at a lower horsepower draw. So we have to ensure in parallel operation that we do not exceed the horsepower draw need for that single pump when it operates by itself. The same thought applies to parallel pumps of unequal size, one large and one small, when the pumps operate either singly or in parallel. In this case, again, we note that each pump must operate at the same head, but for this circumstance, each pump delivers a different flow rate to the system. So at a constant head, we take the flow rate from the small pump, in this case pump B, add that to the flow rate for pump A to achieve a flow point as described by point C. And we can do this in such a manner that we finally develop the paralleled pump curve when both pumps are in operation, which is a hump, if you will, onto the large pump. Striking a system curve through this point, we can determine that the larger pump will be operating at point 2A, the smaller pump at point 2B, and that we are delivering flow rate to the system as described at point 1. Now, if we operate only with the single large pump, we'll be operating at the intersection of the system curve with that pump curve at this point, and if we operate only with the single small pump, without operation of the larger pump, we would be operating on the pump curve as illustrated here. Again, we must make sure that our horsepower capabilities for these pumps are equal to the required need for the pumping situation. This would then conclude the basic discussion on system curves. The basic discussion having covered only closed-loop systems, single and parallel pumps, but did include a discussion, if you will remember, on stock pumps.